Non-silicates, although not as common by volume worldwide as silica minerals, are important because locally, especially in the surface, there can be large amounts of them and an important part of the rock forming process. And even where they're relatively rare compared to their silica containing counterparts, they often are associated with important metal ores and represent critical indicators of interesting geologic processes taking place. While most of these form very near the surface, others will form when there's water down deep, because water at high temperatures can react with a wide variety of anions and cations that it will not react with as vigorously at near surface temperatures and pressures. The first example of these, and probably the most common, are carbonate minerals. This is when you have carbon trioxide, or CO3, an anion ionically bonded with a cation, such as calcium and sometimes also magnesium. There are a few others, but for this class, these are by far the most common. And calcium carbonate, or calcite, is an important constituent of limestone. Indeed, most limestone is made of calcite. Now, the carbonate anion arrives not necessarily from the rocks beneath, but from the atmosphere above. Carbon dioxide will actually react with rainwater, giving you carbonic acid. This carbonic acid makes the rainwater a little more effective than it would otherwise be at breaking down the ionic bonds in certain igneous rocks. And this anion then will join some of the cations that result from this breakdown process and form calcite. If there's magnesium present and the reaction conditions are right, you'll get a second type of carbonate rock known as dolomite, pictured here on the upper left. The addition of the magnesium cation to the system tends to make the rock just a little more stronger and a little bit more resistant to erosion, thus those tall spires you see in the picture that are known as the Dolomites of northern Italy. Now, another rock that is a consequence of water near the surface is halite. As we know, our oceans contain about 35 parts per thousand of sodium chloride. But you've never probably wondered, where does this salt come from? Simply put, the reaction of that slightly acidic rainwater with many of the earlier described rock-forming minerals will preferentially liberate the cation of sodium as well as the anion chlorine, both of which tend to be very quick to break down the way and the crazy cat lady breaks down in the presence of Mickey Mouse. However, when the water gets removed through a process such as evaporation, it is often this halite or sodium chloride that is left behind, such as you see in the lower picture. That, by the way, is a friend, close colleague of mine, operating some meter surveying a dry lake bed in Bolivia. Interestingly enough, another mineral that is very common here, a cation that's very common not too far below here, is lithium, which occupies a similar place in the periodic table to sodium. Just a bit of interesting trivia, but to further illustrate the ionic bonding taking place here and its role in the formation of this very flat lake bed. Now, as bodies of water get progressively saltier, especially if there's the presence of sulfur in the weathering process, you often get sulfates. Calcium is a cation that's also pretty easily liberated from its parent mineral, and in water will sometimes combine with SO4, sulfur sulfur 4 oxide, the anion, to create gypsum. Now, if it's on a lake bed, you'll just see a crust that's sort of clear and does not taste like your conventional salt, will be a bit more bitter. But if this crust gets blown, it can create some beautiful white sand dunes, such as these seen at White Sands Monument in New Mexico. Underground, if the gypsum crystals have a longer time to grow and are in more optimal conditions, if there's a supply of sulfur, you can get some very large crystals, such as the Cave of Swords. These are technically selenite, but very similar. There's also, in this particular mineral, a little bit of water. One of its uses, we do have quite a bit of it in the eastern part of San Diego County, out by Ocotillo and Plaster City. Technically, it's Imperial County, but... And indeed, the reason Plaster City is because there is extensive gypsum deposits in that area that are mined for the making of plaster. Now, these next minerals represent more commonly covalently bonded phenomena, such as your oxides and sulfides. So in the upper right and lower left, you'll see two sulfides, both of which form probably at a little bit of depth and involve flow of fairly hot water through cracks and pore spaces in deeper rocks, often near bodies of magma. The water preferentially strips away the sulfur and the metals, which don't tend to like to form bonds with some of the other minerals present in the rock, but do form pretty good covalent bonds with one another. You notice both these have a sort of cubic habit, and both look kind of metallic. Galena, the lower left, is lead sulfide. The upper right, pyrite, is iron sulfide, and has sometimes been mistaken for gold, such that it is known as fool's gold. Another important thing with pyrite for San Diego County is not that we have great deposits of it, but often where it occurs, you also get soils that are very high in arsenic, which can be a health hazard, though is effective at killing certain insects if it doesn't kill you first. Now, below the second class of ionically bonded minerals are your oxides. While these definitely occur in the deep down, they often also occur at the surface. Hematites, one of the most common minerals we find occurring near the surface when oxygen in the atmosphere reacts with iron in water that has weathered minerals that formed at greater depth, forming this sort of reddish metallic crust. Often when you see a sort of reddish color to soil, or if you notice that the soil gets very hard at not too great a depth and there's a little bit of reddishness, that's probably iron oxide or hematite that you're looking at. Now, another one that's important for San Diego County is magnetite, manganese oxide. This forms in a number of igneous rocks or deep magma chambers in our county, but also tends to be fairly resistant to weathering. So even as those rocks break down, you'll see lots of magnetite in the black sand on San Diego County beaches. Now, another one of these can also be a gem. In fact, many of the great gemstones are oxides, like corundum or rubies and emeralds are all examples of oxides. So it's a fairly diverse class, and again, not necessarily common by volume, but sometimes, in the case of hematite or magnetite, can be quite widespread in the right conditions. Now, finally, we get to those elements that don't really combine very well with other elements or combine exceptionally well with themselves in the right conditions. A couple examples of these are sulfur, pictured at the left, elemental carbon, pictured by the raw diamond in the upper right, or copper. These, again, tend to be concentrated by fluid flow in the right types of temperature and pressure conditions. In the case of diamonds, extreme pressures. In the case of copper, often heavy amounts of fluid flow that favor copper crystallizing on existing copper structures. All these are referred to class of native elements, important as ores, important as gemstones, and other resources.